Preparing for a technical interviews at LTIMindtree interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How does object-oriented programming support maintainable enterprise applications? Object-oriented programming organizes software around objects that combine state and behavior. I use encapsulation to protect data, abstraction to expose only necessary operations, inheritance cautiously for genuine hierarchies, and polymorphism to substitute implementations behind interfaces. For example, a payment service can accept different payment providers without changing business logic. This improves testing and extension, although excessive inheritance creates tight coupling. In enterprise systems, I generally prefer composition and interfaces when designing flexible modules. While answering, explain encapsulation, inheritance, polymorphism, and abstraction. Connect each principle to maintainability, reuse, testing, loose coupling, and a practical Java or C# enterprise example. Question 2. What is the difference between an interface and an abstract class in Java? An interface defines a contract that unrelated classes can implement, while an abstract class can provide shared state, constructors, and partial behavior. A class can implement multiple interfaces but extend only one class. I choose an interface when I need interchangeable implementations, such as several notification providers. I choose an abstract class when subclasses share meaningful lifecycle logic. Modern Java interfaces can contain default methods, but I still avoid using them to hide excessive implementation complexity. Make sure to cover contracts, shared implementation, constructors, state, multiple inheritance of type, default methods, access modifiers, and how you would choose between them in an LTIMindtree project. Question 3. How would you identify and optimize a slow SQL query? I begin by reproducing the issue and capturing execution time, row counts, and the database execution plan. I check for full table scans, expensive joins, missing or ineffective indexes, stale statistics, and functions applied to indexed columns. Then I reduce selected columns, filter early, optimize joins, and consider keyset pagination for large result sets. I validate with realistic data and compare plans afterward. I also parameterize queries to improve security and plan reuse. In your answer, talk about execution plans, indexes, joins, filtering, cardinality, statistics, pagination, avoiding unnecessary columns, parameterization, and measuring improvements before and after changes. Question 4. Explain normalization and denormalization. When would you use each? Normalization separates data into related tables to reduce duplication and prevent insert, update, and delete anomalies. I use normalized schemas for transactional systems where consistency matters, commonly through the third normal form. Denormalization intentionally duplicates or precomputes data to improve read performance, which can help dashboards or high-volume reporting. The trade-off is more storage and synchronization complexity. I make the decision from measured workload characteristics rather than denormalizing prematurely. Be sure to mention data redundancy, update anomalies, normal forms, transactional integrity, read performance, storage trade-offs, reporting workloads, and how indexes or caching may reduce denormalization pressure. Question 5. How do you handle exceptions in a production Java or .NET application? I handle exceptions at the layer best positioned to recover or respond. I use specific exceptions for expected business failures and centralized middleware or global handlers for consistent API responses. Logs include correlation IDs, operation context, and stack traces, but never secrets or personal data. I use try with resources or equivalent cleanup mechanisms and retry only transient failures with bounded backoff. I avoid empty catch blocks because they conceal defects and complicate production diagnosis. Focus on checked versus unchecked errors, meaningful exception types, centralized handling, logging context, user-safe responses, retries, correlation IDs, cleanup, and avoiding swallowed exceptions or sensitive information in logs. Question 6. What principles would you follow when designing a REST API? I model endpoints around resources, use HTTP methods consistently, and return meaningful status codes. For example, POST creates a resource, GET retrieves it, and PUT or patch updates it. I validate input, provide a stable error structure, support pagination and filtering, and design idempotent operations where retries are possible. Authentication and authorization remain separate concerns. I also plan versioning and backward compatibility early, because client integrations often outlive individual service releases. In your answer, cover resource-oriented URLs, HTTP methods and status codes, idempotency, validation, pagination, versioning, authentication, error formats, backward compatibility, and observability. Question 7. How would you secure a web application against common vulnerabilities? I start with threat modeling and apply defense in depth. Parameterized queries prevent SQL injection, output encoding reduces cross-site scripting, and CSRF protection secures state-changing browser requests. I enforce strong authentication, least privilege authorization, secure cookie settings, TLS, dependency patching, and centralized secrets management. Sensitive events are logged without exposing credentials. Finally, I include static analysis, dependency scanning, penetration testing, and security regression tests throughout the delivery pipeline. Make sure to discuss input validation, output encoding, parameterized queries, authentication, authorization, CSRF, secure headers, dependency patching, secrets management, logging, and security testing aligned with OWASP risks. Question 8. What is the difference between processes and threads, and when would you use each? A process has its own address space and resources, while threads share memory within a process. Processes provide stronger isolation but communicate more expensively through mechanisms such as sockets or queues. Threads are lightweight and efficient for concurrent work, but shared state introduces synchronization risks. I use processes when fault isolation or security boundaries matter, and threads for coordinated tasks inside one service. For CPU-heavy work, I also consider language runtime constraints and parallel execution support. While answering, explain memory isolation, communication overhead, scheduling, failure containment, concurrency, synchronization, scalability, and examples where processes or threads are more appropriate. Question 9. How do you prevent race conditions in concurrent code? A race condition occurs when results depend on unpredictable operation timing. I first reduce shared mutable state through immutability or message passing. Where sharing is necessary, I use atomic operations, appropriately scoped locks, or thread-safe collections. In database workflows, I select suitable transaction isolation and enforce constraints at the database level. I keep locks small and consistent to reduce deadlocks, then test with stress and race detection tooling instead of relying only on normal unit tests. Be sure to mention shared mutable state, atomic operations, locks, concurrent collections, immutability, transaction isolation, deadlocks, lock scope, and testing under realistic concurrent workloads. Question 10. How would you design a reliable microservices-based application? I define services around business capabilities and give each service ownership of its data. I use synchronous APIs when an immediate response is required and events when decoupling or resilience is more valuable. Every remote call needs timeouts, bounded retries, circuit breaking, and clear failure handling. Centralized logs, metrics, traces, and correlation IDs support diagnosis. Microservices are not automatically better. I choose them only when independent scaling, ownership, or deployment justifies their operational complexity. In your answer, discuss service boundaries, data ownership, synchronous versus asynchronous communication, timeouts, retries, circuit breakers, observability, deployment independence, eventual consistency, and operational complexity. Question 11. What is the role of Docker and Kubernetes in application deployment? Docker packages an application with its runtime and dependencies, making development and deployment environments more consistent. Kubernetes orchestrates containers by scheduling them, restarting failed instances, exposing services, managing configuration, and supporting rolling updates and scaling. I build small, immutable images, scan them, and keep secrets outside images. Readiness probes control traffic, while liveness probes detect unhealthy processes. The key distinction is that Docker packages workloads, Kubernetes manages them at scale. Focus on image consistency, container isolation, registries, deployments, services, configuration, secrets, health probes, scaling, rolling updates, and the distinction between packaging and orchestration. Question 12. Explain a CI/CD pipeline you would implement for an enterprise project. A commit should trigger compilation, dependency checks, unit tests, static analysis, and security scanning. Successful builds produce immutable versioned artifacts stored in a repository. Integration and contract tests run before promotion through controlled environments, with approvals where risk requires them. Deployment should be automated, observable, and reversible using blue-green or rolling strategies. I monitor key business and technical metrics after release and define rollback criteria before production deployment, rather than reacting afterward. Make sure to cover source control, branching, builds, unit and integration tests, static analysis, artifact repositories, security scans, approvals, deployment automation, rollback, environment promotion, and monitoring. Question 13. How would you troubleshoot a production API whose response time suddenly increased? I first confirm the increase using latency percentiles, error rates, throughput, and affected endpoints. Distributed traces help separate application time from database or downstream dependency time. I check recent deployments, traffic changes, connection pools, CPU, memory, garbage collection, and query plans. Immediate mitigation might involve rollback, scaling, rate limiting, or disabling a safe feature. After recovery, I document the root cause, add targeted alerts and tests, and verify the fix under representative load. In your answer, describe symptom confirmation, dashboards, distributed tracing, recent changes, dependency latency, resource saturation, database plans, traffic patterns, mitigation, rollback, and root cause prevention. Question 14. What are the differences between unit, integration, and end-to-end testing? Unit tests isolate a function or class and run quickly with controlled dependencies. Integration tests verify collaboration with components such as databases, queues, or external contracts. End-to-end tests exercise a complete business flow through deployed layers. I keep most tests at the unit and service levels because they are faster and easier to diagnose, while retaining focused end-to-end coverage for critical journeys. Test doubles help isolation, but real infrastructure tests catch configuration and integration defects. Be sure to mention test scope, speed, isolation, external dependencies, confidence, mocking, test data, maintenance cost, and how a balanced test pyramid supports continuous delivery. Question 15. How would you explain the solid principles using a project example? In an order system, single responsibility keeps pricing, payment, and notification logic separate. Open-closed design lets me add a new discount strategy without changing stable checkout code. Liskov substitution means every payment implementation honors the same contract. Interface segregation prevents clients from depending on unused operations. Dependency inversion makes checkout depend on payment and repository abstractions, injected at runtime. Together, Solid reduces coupling and makes changes safer, although applying it mechanically can create unnecessary abstractions. While answering, connect each principle to concrete design decisions: focused responsibilities, extension without modification, substitutable implementations, small interfaces, and dependency inversion through abstractions. Question 16. How would you solve a coding problem involving duplicate elements in an array? I would first clarify whether I need the first duplicate, all duplicates, or only a Boolean result. For a general array, a hash set provides expected O, n, time and O, n, space. Scan each value, check whether it already exists, and otherwise insert it. Sorting gives O, n log n, time and may reduce extra memory, but changes order unless copied. I would handle empty input and null values explicitly, then justify the choice using constraints. In your answer, clarify constraints, compare sorting and hash-based approaches, state time and space complexity, consider memory limits, and explain edge cases such as null, negatives, and repeated occurrences. Question 17. What data structures would you choose for an LRU cache? An LRU cache needs constant time lookup, insertion, update, and eviction. I combine a hash map from key to node with a doubly linked list ordered from most recently used to least recently used. Access moves a node to the front, and exceeding capacity removes the tail node. This gives expected O(1) operations. In production, I would also address synchronization, expiration, memory limits, serialization, metrics, and whether a distributed cache is required. Focus on required operations, hash map lookup, doubly linked list ordering, O(1), complexity, eviction semantics, thread safety, capacity handling, and how a production cache differs from a coding exercise. Question 18. How would you design a batch data processing solution for a client project? I would divide input into manageable chunks, validate records early, and process each chunk within clear transaction boundaries. A checkpoint records completed work so failures resume safely, while idempotent operations prevent duplicates during retries. Invalid records go to a dead letter store with actionable reasons. I would control parallelism based on database and downstream capacity, expose progress and failure metrics, and reconcile totals after completion. The design should favor recoverability over maximum theoretical throughput. Make sure to cover input validation, idempotency, chunking, checkpointing, retries, dead letter handling, transaction boundaries, parallelism, monitoring, reconciliation, and protection against duplicate processing. Question 19. How do you approach requirements that are ambiguous or changing during a client engagement? I begin by identifying the business outcome, users, constraints, and measurable acceptance criteria. I document assumptions and ask targeted questions rather than implementing vague interpretations. For uncertain workflows, I use a small prototype or example-driven discussion to expose gaps. When requirements change, I assess scope, dependencies, cost, and risk, then realign priorities with stakeholders. Clear traceability from requirement to design, tests, and release helps protect quality while remaining responsive. In your answer, discuss clarification questions, assumptions, acceptance criteria, impact analysis, prototypes, stakeholder alignment, traceability, prioritization, and communicating delivery risks early. Question 20. Describe a technically difficult project problem and how you resolved it. On a previous project, an integration service intermittently timed out during peak traffic. I analyzed logs and traces, reproduced the pattern with load tests, and found connection pool exhaustion caused by slow downstream calls. I introduced strict timeouts, bounded retries, pooling changes, and monitoring, then coordinated a staged release with the team. P95 latency fell substantially and failures became visible earlier. The experience reinforced that resilience controls and observability must be designed together, not added after incidents. Be sure to structure the response with context, your specific responsibility, investigation, technical options, decision rationale, measurable result, collaboration, and what you learned for future delivery. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.